Hello everyone, I'm Reza Tangisa and this is the third episode that I'm going to explain the common error in Abaqus, and in this episode I'm going to mostly talk about the step and incrementation in the software. Continuing with the introduction, we define the type of our simulation by using a step module in Abaqus, and each step has different feature which we require to know the details so we avoid error during the simulation. The software only uses the default value, but it is most likely for us to change the value due to our simulation requirements. Here we're gonna explain each feature with an example on how we can avoid fix those problems, and after that, by the end of the video, by the end of each model, we might be able to explain some of the accuracy that we can get from the results. Okay, explaining from the step, we already explained this part in our past video, as you can see on top. If you're interested, please visit our video from our channel, but we're gonna explain it one more time here. So starting with the time period is the duration of our simulation. For example, a tensile test might require 10 seconds, and so that's where we define our time period. But the software requires to divide each time step to increments in order to solve it. So that's why we have multiple increments for each step. Continuing to the next tab, the incrementation, we are able to only control the size of the first increment. So the first increment, we define the value of it. As you can see in here is 0.1, but for the rest, the software change the value. It might decrease or increase the size of it due to the convergency. And but we might be able to control the minimum or maximum size of it, which we will explain in the next slide. Before continuing to next slide, I would like to mention that because we are going to define the first value, if we define a large value, it might cause some error because it might be too large for solver to solve the simulation, so it returns an error. We're gonna explain this error in Abaqus by showing you with an example. Moving on to the next one, we have the minimum one. By default, it is the value shown in here. So as I mentioned, we only can control the size of this one, but we can ask the software if the size of increment decrease to a certain value, it stops the simulation. For example, if we have 10-second simulation and our increment size decreased to 10 power minus 10, we require more than 10 power 11 increment to solve. So we know it might take years to solve the simulation, so that's where we ask the software to stop the simulation so we can check the problem. It's a criteria to stop the simulation, and it happens when the simulation, the increment size goes below the specific value that we define. And we're gonna explain this part in our model as well. So moving on to the next one, which is the maximum one. It doesn't create any problem, but it controls the maximum size. For example, the software might be able to find the simulation easy to solve, so it increases the length of the increment. As you can see here, the second one gets larger, and it's larger than the value that we define. And if it happens, it changes the length of the second increment equal to the maximum one. So, but it doesn't stop the simulation. We skip this part because it doesn't create any error during our simulation. And at the end, we have the maximum number of increments, which by default is 100. So if the number of increments the software requires for solve the model increases more than the 100, the solver stops the simulation. We could change the value in order to stop the simulation. Personally, I would define a big value here in order to avoid any problem during my simulation. And again, we're going to explain this problem with a thermal and mechanical example in Abaqus. Moving to the last slide, we have the creating step in Abaqus. And whenever we need to define the step, we need to define the previous step, which is initial in this example. And after that, we need to define the type of step. As we explained, it might be a static, dynamic, heat transfer, and it depends only on our simulation. We're not gonna explain how to define creating a step, but if you're interested, we can create a video and you can let us know by commenting this video. Okay, now we're ready to move on to or explain each problem by showing an example. To go over the problems and error, I have created 3 thermal models. This is the additive manufacturing or welding model that we've been created previously, and you can find it from the video that's been shown here. Just in case if you're curious to know how we created this model, I'm going to go over the model quickly. So this is the geometry that we've been created, and we created a partition here. For the property part, I changed the property for conductivity and specific heat, so we can have temperature dependent material. However, I didn't change the density, and it's temperature independent. For the assembly, you can see the center of coordinate system. For a step, I've created 5 steps. I'm not gonna go in details because in each model I change some part of the steps so we can go over the errors individually. But you can see each step is 1 second and we have 5 of them, so the total simulation time is 5 seconds. For interaction, I'm adding the material. As you can see, in each step we are adding a portion of the material, and in load module you can see it's a surface heat load, so we are working on the Gaussian heat input. And on mesh section I use the thermal elements. This feature is similar for all 3 models. However, the step details are different between each model, and we will go over them separately. So for the first model, if you go to the detail, you will see the time period is 1 second. The incrementation, you can see the maximum number of increment, the initial, minimum, and maximum time increments, and the maximum allowable temperature. You can see we all define it. And I already run the simulation, and if you run the simulation, you will see the first step, it goes smoothly. In the second one, we have some atoms. As you can see here, it's a bit of problem in convergency, but the solver managed to go through, and after that it continues smoothly up to the third step. So when it enters the third step, we have 5 errors, and it causes too many attempts. In order to fix it, we already know that the error started right away after starting the third step. We have 2 approaches. The first approach that we could do is from the step part that I'm going to explain it, and the second part is changing the solver. So I already explained this part that you can change the solver settings, so you could go easily to here and change the number of attempts here, but I don't recommend it because there is a easier way to fix the problem by changing the initial time. So as I explained in the PowerPoint file, the initial increment is the first increment that Abaqus decide to start the step. So here I use the initial increment of 1, which is equal to the time period. So because the initial increment is large, it's exactly same size of the time step, the solver cannot solve the model, and it requires to make the increment smaller and smaller, and after the 5th try it returns the error. So what we could do is we could reduce the initial increment size, as I'm doing here. I'm gonna repeat this for all steps, and then I'm good to go and run the simulation. As you can see, the first model is being completed. We had a few atoms, but they are during the process, which is okay. Already we can see, for example, here sometimes we reach the 3rd attempt. So if you see you have close to 5th attempt or 6th attempt, or you face too many attempts in middle of the simulation, you also can go to the approach that we explained previously, that changing the number of maximum attempts. Okay, this is the first part. We can go for the next one. You can see that the second part is already been completed, but I wanted to explain the feature in step, so that's why I'm gonna go over it quickly. So for the first one, you already see we had 85 increment for each step. For example, step 6, and for example, for step 5, it's 75. It's more or less around between 70 to 80. But in the second mod part, we can see the number of increments is significantly larger than the previous model. And if you look at the increment size, it's smaller than the previous model. Checking the results, you can see that the heat source is very smooth. I reached to the end of it. In total, it requires 2,000 increments to solve the simulation. We go to a step to check the feature that causes this problem. We open it, and we can see everything's fine, but here I change the maximum allowable temperature per increment. What does it mean is when an integration point experience 10 degrees centigrade change in the temperature, it reduces the increment size to make it less than temperature. For example, if all elements are at 100 degrees centigrade and one of the elements changes the temperature from 100 to 112, it changes the increment to a smaller value, so it will be, for example, 106, and the next one it can go, for example, 112, so it add another 6. So delta T, or the temperature variation, cannot be more than the 10 degrees centigrade. So that's why it requires a lot of increment. So you could increase it to a larger value, so you need less number of increments. However, using a smaller value increases your accuracy, because you can see the temperature variation very smoothly. Let me show you to you. Here you can see, by showing the animation, it's very smooth. But going to the first one, it's not as smooth as the first one. Like, it's a bit different, and we only need a 380 increment. So if you require to have a better accuracy and you don't care about the computational time, you can change the value to a smaller value here, so you can have a more and better increment simulation. But I personally work with the maximum increment size, so I won't let the simulation to use many large elements. Okay, this is the second model, so now you all realize what does this blank do. I'm not going to over this one because it's not very necessary for the simple thermal models, so I'm going to skip this part. I'm going to go to the third part. The third model, you can see it's been aborted. If we go to the error, if you look at it, you will see that it says too many increments needed to complete this step. So when you face this problem, you go to the step and you need to change the number of increment here. So the maximum number of increments has been set to 10. So if the step requires more than 10 increments to solve the simulation, it will abort the simulation. That's why I personally use a large value, so I let the simulation use increment as much as it wants, so the simulation can continue. So now I can run the simulation and see the results. As you can see, the simulation has been completed. We can see it's went to the last step and everything's fine. Now we can go to the results and see the heat movement. Yeah, everything's fine here. So after here, I explained the thermal models, and I can switch to the mechanical one. There are a few more details that I would like to explain. So now we move to the other two models for the mechanical part. These are two mechanical models, and I wanted to explain the geometry and the feature first. So starting with the part, you can see the geometry, the property. You can see the elastic material. I took the exact model from the previous video we saw for the material property, and I didn't change anything here except the material property for plasticity. The 200 value has been used here for model 1. Assembly and step. For the step, we only use one step with the duration of 1 second. I didn't define anything in interaction. For the load, you can see I define one uniform load on top of it with the value of 200 megapascal, and with the amplitude that I will show it to you. So this is the amplitude that I defined. So you can see in the first 0.01 second we apply the entire load on top of it, and we move to the boundary condition. We define 3 type of boundary condition caster at the bottom part, and we fix the size of it. Okay, we go to mesh. For the mesh, we only use 3D reduced integration. It's been checked, and we can go to the job and to see what happened in their model. So job 11, I'm going to check the monitor. You can see it went up to the 3rd increment here, but it stopped, and the error we given is like the increment required is less than the minimum specified. So we go to a step, we go back to a step, and we open the step that we define. You can see the minimum step that we use is only 10% of the initial one. So what I recommend you, in many models, the minimum value is not a concern for us. We can let the simulation use increment as much as it requires. So that's what I always do. I use a very small value for minimum increment, and I pick the maximum large, and I let the simulation run and use as much as it use increments as much as it wants. So let me run the simulation again so we can see there if it works. Okay, as you can see, the job is completed. It only required 27 increments, and we had a few attempts here. It's okay, and we can see the results. You can see the results that the stress distribution is changing during the time, but after the few frame does not change anymore. So after this 0.01 second, you can see that the stress doesn't change because the value of the load in the table we define is set to 1. So let me get back to the load. Here in amplitude, we define after 0.01 the amplitude, should set as 1. So all the load that we define, which is 200 megapascal, is being applied from 0 to 0.01, and after that it doesn't change. That's why we don't see any different stress distribution. Okay, this is the first part. We move to the second one. The second model is similar to the thermal model that we explained, that it has the same problem. I just wanted to show you, in many cases we can find a similar error for the thermal and mechanical model. So if you look at it, it says too many increments needed to complete this step. Go to the incrementation. We can see it started with a few attempts but didn't continue after number 10. So it's exactly like the thermal model I explained previously. We could have easily changed it by just adding a value here to larger value, like more than 10, and we could again run the simulation. Perfect, the simulation is over. You can see it's been completed. It's required again 27 increment, and you can see the results again. So the only change that we needed to apply for the increment, it was the maximum number of increment, and by changing that value we could have solved the simulation. So this is the part for the step. There are many different detail that you would have want to consider. So if you have any question regarding the step, please let me know so I can make a video and I hope I would be able to help you with your problem. For the next one, I would explain the mesh and how the meshing will affect your results. Until the next one, bye.
This video was made by Reza Tangisani. To find his contact information and his updated resume, please visit our website at hyperlyceum.com. Reza is an expert in Abaqus, Python, Fortran, SolidWorks, and a few other engineering software. To plan an online session and discuss industrial and academic projects, please use the provided email under Reza's contact. The cost of projects vary depending on complexity of the work and can be discussed in advance. We look forward to working with you.